Hello, welcome to a new episode of Plan C, Ocean Interventions to Address Climate Change. As always, I'm your host, Will Burns. I'm co-executive director of the Institute for Responsible Carbon Removal at American University, and I'm joined by my co-host, Anna Madlener, who is the MRV manager at the Carbon to Sea Initiative. Hi, Anna.
Hi, Will. It's so nice to be back with you after 2 episodes of in-person conference hosting.
Indeed, but you've had great replacements.
I did, yes, but Danny and I were having fun about assuring our guests that will be back.
Yeah, that sounds more like a threat, but anyway. Today's guests are 2 representatives of the startup, Ebb Carbon, an ocean alkalinity enhancement company that operates in Washington State. Kyla Westphal is the Vice President of External Affairs, and Mallory Ringham serves as the lead oceanographer and head of MRV. And they're joining us today to share their journey in securing a permit for operations this summer and for going forward, as well as their monitoring plans for this trial. For our avid listeners, this should also be an exciting update regarding Ebb's journey and progress since November of 2023, when the late Matt Eiseman and Francis Simpson Allen joined Plan C to introduce Ebb's work. To no one's surprise, probably, I'm really keen to start diving into regulatory and permit details of the project. Anna, what are you excited about talking about today?
Well, to no one's surprise, I want to discuss the monitoring plans a bit more in detail. So those that are in the permit, and in particular, how those requirements overlap versus deviate from what is, I guess, valuable to measure from a scientific perspective. So permit and monitoring talks today.
Very cool. All right, then, shall we kick off the episode?
Yes, let's do it.
Welcome, Mallory and Kyla. Thanks for joining us. Let's start off with a round of introductions. Kyla, would you like to start?
Sure. Yeah, thank you for having us. So I'm Kyla Westphal, and I lead external affairs at Ebb Carbon. To give you a little peek into my background, I really started my career working for a U.S. senator in California, and that role was really all about meeting with constituents, voicing their priorities. And I share that because I think it has a direct connection to the work that I do today with Ebb Carbon. Since then, I've spent about 15 years working on emerging climate solutions, and I've really kind of developed a specialty working at the intersection of technology and humanity, which is really what I like to call the hardest part of the problem. At Ebb, I've spent a big chunk of my time here developing our approach to safe and responsible deployment. And we really see that grounded in 3 pillars: permitting and regulatory approval, ecological safety, and stakeholder engagement. I really look forward to digging into those with you today.
Great. Mallory?
Hi, glad to be here. I'm Mallory Ringham. I'm a chemical oceanographer. So my role at Ebb Carbon is as lead oceanographer, and most of what I think about is measuring, reporting, verifying how much carbon removal we've actually done through our process. My background is all in traditional oceanographic methods to understand carbon dioxide in seawater. So I spent most of my academic career building carbon sensors, deploying them in coastal environments, understanding facets of ocean acidification that's related to climate change. And I pivoted into ocean alkalinity enhancement to work specifically on applied science solutions to our climate problems.
All right. Well, let's just get into it then. What I want to emphasize at the outset is we're not going to do a concentrated deep dive on Ebb Carbon's approach from a technological perspective. We suggest anyone who isn't familiar with this approach to listen to our previous episode with Ebb in 2023. But to set the stage for today, Kyla, could you introduce Ebb Carbon as a company and a bit about the upcoming trial in Washington State?
Sure, absolutely. So Ebb Carbon is a marine carbon dioxide removal company, and our specific approach is called electrochemical ocean alkalinity enhancement. And the core insight from really one of our founders, the late Matt Eiseman, is that we need to work with nature's natural processes to capture and store excess CO2 from the air. So in our case, this is the ocean, which is one of the planet's largest carbon sinks, and the inorganic carbon cycle. And so the technology we've developed is one that can solve two climate-related problems at the same time: excess CO2 pollution in the air and excess acidity in the ocean. We've been working in Washington State for many years now, actually, and our work there goes back to some of the foundational research that underpins EB that was initiated by Matt Eisenman with the University of Washington. And Mallory can speak much more to this. But since those early years, we've been demonstrating our technology with the Pacific Northwest-National Lab, PNNL SQUIM. And along the way, we learned this is the only national lab with marine labs. And then later this year, we are going to build on the work that we've done in that region and operate a pilot system just down the road from SQUIM in Port Angeles, Washington. And I will say that, working in Washington has been very intentional. Not only is there the world-class expertise at the national lab, there's also very acute climate-related impacts that are felt there locally, specifically ocean acidification.
What stage does this trial represent in the company's roadmap to potential full-scale deployment of this approach?
I mentioned we have demonstrated our technology for over a year now at PNNL SQUIM. And so this next step for us is a small-scale temporary pilot. It's a first-of-a-kind pilot, and so it really is, our proof of concept on many dimensions, operating the technology in the real world, advancing the science, and doing this, in partnership with community and gaining social acceptance along the way.
So speaking of community, during the recent Ocean Vision Summit, which we also covered in a previous podcast episode, at that summit, AppCarbon was praised for your community outreach work in Washington State. Can you describe the work that you've done in a little bit more detail and how you responded also to community feedback in particular?
Yeah, absolutely. And thank you. We take our work in this realm very seriously. It's really part of our technology design process, which I can speak to a little bit later. In Washington State, we started our engagement work very early in the journey, and we really see it as rooted in three kind of key elements. The first is trust building. So really taking the time to build relationships and trust with all sorts of really critical stakeholders, including tribes, regulators, local community groups. And I think, this can't be underlined enough, particularly for a first-of-a-kind technology that, folks are really learning about for the first time, whether they're regulators, whether they're in the community, whether they're tribes. And the second element is, aligning with community priorities. So I mentioned the intentionality around developing this technology in Washington State and kind of the acute impact of climate change that's felt in that region, which is ocean acidification. 30% of species in Puget Sound are vulnerable to acidification, and the shellfish industry in particular has been hit hard by this in Washington State. And so we spent a lot of time meeting with the shellfish industry, understanding how acidification is impacting the tribes, and understanding the state's priority around finding solutions to acidification. And that was really a conversation that, we could enter that was already happening, that was highly relevant in these places. And then third, prioritizing tribal engagement. We quickly learned that treaty tribes in Western Washington are absolutely critical to any project development. They're co-managers of the natural resources there, and both the federal and state governments must consult treaty tribes about any state action, like issuing permits that will potentially affect them. So to kind of bring this to life a little bit and get into the nitty gritty here, one of the very first things we did was kick off broad engagement with the Puget Sound Treaty Tribes. And this was before we had any particular site identified, but we knew we wanted to build on the knowledge and expertise that we had developed and are developing in the area. So specifically, we presented to the Northwest Indian Fisheries Commission to really share information about our technology, raise awareness of who we are, show up as, genuine humans trying to solve climate-related problems, learn from them, address questions, and see if there was any, opportunity to seek partnership and advance tribal participation in MCDR. In terms of how we have responded to feedback, and particularly tribal feedback, one of the things that we are particularly proud of is a partnership we have with a local Indian tribe, where we developed a novel salmon study using coho salmon, juvenile salmon that were donated by that tribe for this purpose to really start to simulate in a laboratory environment what those juvenile salmon might experience in the wild. And, this work was a direct result of the conversations we had been having since, day one, where the tribe was very interested, again, because this was a first of a kind technology. And, well, gosh, this has never been done before. How are we going to really understand what the potential impacts are in the water? And so that's something that I think is a really unique aspect of the work that we've done in Washington State.
I would agree. And I think I want to hone in on this a little bit. I believe that you also shared at the summit that truly, if the tribal communities had not approved, even before selecting a site, that as a company at that point, you were willing to sort of cancel a project. It takes a lot to say that. And I think it takes even more to actually come to the agreement that this is your stand. So I wonder if you could share a little bit more about what it took internally also to get to a point where you were willing to promise that and able to promise that.
Yeah, I think this is, a credit to our founding team, which has worked on emerging kind of innovative technologies in the past and has experience with, what it feels like when projects are successful and when they're not. And we quickly aligned as a team and understood that it was clear that if the tribe did not want us there, we were not going to be successful. It was really just as simple as that. And so by, pivoting into this frame of mind around, hey, tribal engagement, stakeholder engagement, we think of this as part of early on in the design process for our technology and this pilot that we were going to deploy. It was only going to improve the outcomes. And that's really how we approached this.
That makes sense. And so now that the project is permitted and will be taking off and will be ongoing, what will you continue to do in that regard?
So we have some ongoing research that we're exploring with the tribal partners. And so we're looking forward to moving beyond salmon and starting to look at some experiments with shellfish. And Mallory can speak much more fluently to that. And we also are developing some local partnerships. So there is a marine center called the Fierro Marine Center located in Port Angeles. And so we're working with them to try to develop some educational materials that they can host at their facility, which is all about, understanding the local ecosystem and is really a hub for education for that community. And then we also have some neighbors right nearby our site who hold it's essentially a yacht club, and they have sailing lessons. And so really thinking through how we might be able to also provide educational content to that community as well.
Yeah, I think that idea of co-development and kind of reflexive response to stakeholder needs is really important. And you're right. It's not only the right thing to do, but it's probably critical in making sure that these kind of projects can work. So I think that's interesting. So let's move on to what really excites me, the whole regulatory landscape that you've encountered in this case. And I just want to talk a bit about the regulatory journey of the Makoma project that we're talking about in a little more detail. And first of all, for listeners who don't spend a whole lot of time in the realm of U.S. environmental laws and regulations, EB had to secure something called a National Pollutant Discharge Elimination System Permit, or MPDES, under the U.S. Clean Water Act. And more generally, under the Clean Water Act, discharge of pollutants into waters of the United States, as the statute provides, via a point source, which is a pipe or a channel or a conduit, is prohibited unless you have obtained an MPDES permit. And then this MBTDES permit will generally specify an acceptable level of a pollutant or a pollutant parameter, a chemical or physical characteristic of water in the discharge. Now, the Woods Hole Oceanographic Institution was very recently granted a research permit under another U.S. statute, the Marine Protection, Research, and Sanctuaries Act, to conduct an ocean alkalinity enhancement research program on the East Coast. I was wondering, Kyla, could you explain to our audience why your approach took you down a different regulatory path than the one that Woods Hole encountered?
Sure. And I think you're probably one of the few of us who get super excited about regulation. But now that I've gone through this, I'm kind of there with you. So it's exactly as you've said. Well, the EPA has issued guidance on permitting for MCDR. And so our type of deployment, our type of pilot does discharge from a point source. And that ergo is why it's regulated under the Clean Water Act and requires this NPDES permit. And so this is the path we followed, and we ultimately received the first NPDES permit for marine carbon dioxide removal for Project Makoma, which is the pilot in Port Angeles.
Now, one thing I was interested about, and again, this is kind of insider baseball, but interesting, I think, in terms of how the Clean Water Act works. My understanding in your project is you aren't really adding any, quote, pollutants that are regulated under the Clean Water Act. Can you explain then why your project falls under this statute? What's being regulated in your operation under the Clean Water Act?
Yeah, ultimately, at the end of the day, we are discharging alkaline enhanced seawater. And under the NPDES permitting regime, we need to meet excellent water quality standards at the edge of, these prescribed mixing zones. And there's a whole process that we have gone through in order to understand, when we discharge this alkaline enhanced seawater, what happens in the surrounding waters, in the receiving waters, right? And in order to get an NPDES permit, there's a lot of site assessments that need to be fulfilled and completed. And one of those is what we've called a mixing zone analysis. And so it's really using models and using kind of the permit handbook that's, given by the Department of Ecology in the state of Washington to understand, well, what are the water quality effects we might see as a result of this discharge. And so for us, because we're introducing alkaline enhanced seawater, the pH of that seawater is elevated compared to the receiving water. And that's intentional. That is, in part to address the increased acidification of the receiving water. And it's also what ultimately helps us draw down CO2 from the air and store it safely in the ocean. And so what regulators are looking at for our permit are we able to meet excellent water quality standards at the edge of what is called a mixing zone in terms of pH.
Great. So can you tell me a bit about some of the challenges that you faced in getting the first of a kind permit in this context, and any lessons learned that might be helpful for future companies that are looking to engage in an MCDR approach that would require obtaining an NPDES permit?
Yeah, I would say that the key challenge really all goes back to the fact that this is a first of a kind pilot project. This is a early technology. There's no blueprint for this. While EPA has issued guidance on permitting pathway, which is an excellent help in understanding what the journey needs to look like. Project developers like ourselves, regulators, communities are all doing this for the first time. And so it takes time. I think philosophically, we have a saying, you need to go slow to go far. And I think that's really underpinned a lot of our work in Washington State, whether you're looking at, demonstrating the technology at PNNL as a very first step, to, really engaging with tribes and community groups to help inform what the technology should look like in the real world. All of this, I think, adds up to a lesson of it may feel like it's going slow, but it will go faster in the end, right? As I mentioned, we have the first NPDES permit for MCDR, and I really believe that is a result of the very deliberate, thoughtful relationship, knowledge building that we were able to do in Washington State.
Yeah, I think it's a good lesson, and famous last words. I'm going to bet that these will be expedited a bit more in the future once regulators are more comfortable and see the results of these approaches. And somebody had to start, right? And that's true also in terms of the MPRSA permit, I think, on the other coast. But you can understand why regulators are cautious in this context, and quite frankly, how a lot of these things that we're looking at were never contemplated under these statutes, right? Which makes it difficult in some ways to apply these criteria. But I think the agency did a good job in fitting it into the framework, and the same thing with the MPRSA. So it'll be interesting to see going forward.
Okay, I want to play the other. What did you call it, Will, in baseball? Insider baseball. I want to play MRV insider baseball. I want to sort of pick up something that you said, Kyla, and pivot over, because you mentioned that the permit was very much driven or guided by a mixing zone analysis. And Mallory, I wonder if you can share more about generally your approach to monitoring and modeling for quantification and how that sort of interacts and maps to a mixing zone analysis.
Sure. So to break it down a little bit, the first thing I want to say is that there's a lot of different reasons why we might make measurements around a field site like this. So there's monitoring for compliance with regulatory permits. There's monitoring for the purpose of understanding how much carbon we've removed, and part of that goes towards things like model validation. So I'll separate it out into those categories. So the first piece is the one that is focused on monitoring in regards to our permit. So in this case, as everyone has been talking about, because this is a new effort, operating slowly and carefully and making sure that we learn at each stage is important to everyone in this space, including our regulators. So the way that our permit operates is we have a specific mixing zone, and that is a volume of water that we discharge alkalinity into. We have a measurable impact on seawater chemistry only in the middle portion of that mixing zone. And by the edges of the mixing zone, we must meet excellent water quality standards. So for regulatory purposes, we have to demonstrate that we are following the guidelines of that permit. That means continuously monitoring our input into the ocean. That's the amount and concentration of alkalinity. And then there's a series of water quality parameters that are tracked within the mixing zone, at the outfall, at the edge of the mixing zone, beyond the mixing zone. And those include factors like temperature, dissolved oxygen, turbidity, pH, the things that the state is really interested in that has an impact on marine environment spaces in general. Beyond that, there's collection of samples for total suspended solids, for metals. All of that information is publicly reported to Washington State. In addition to that, our permit requires that we conduct studies for understanding aquatic vegetation within our mixing zone, analyzing the sediment within our mixing zone. So there's a lot of different pieces there that are really made to make sure that we operate in a way that is safe and responsible, given that this project has an impact on water quality within Washington State and all of the different communities that have input in that. So when you transfer this into, okay, what about the other half of the equation, which is understanding what we've accomplished, how much carbon dioxide we've removed, how we've stored it, then that gets a little bit more technical, because the process that we're working with impacts seawater chemistry in the near field and in the short term in a different way than it actually affects carbon dioxide removal. So specifically, we release alkalinity into the surface ocean, and that shifts the way that carbon is stored in seawater in such a way that we make space for atmospheric CO2 to be drawn down into the ocean, right? But the actual movement of carbon dioxide from the atmosphere into the ocean takes some time. The equilibration across that boundary can take anywhere from days to weeks to months to years, dependent on a wide variety of considerations at your site. So this can vary regionally. It can vary with wind speed. It can vary with surfactants on the surface of the water, a lot of different pieces. And the challenge for everyone working in these sorts of open systems is that the ocean is chaotic and there's a lot of background noise and there's a lot of variability. So daily tides, seasons, movement of water masses from a variety of different processes that may be river runoff, it may be a storm, it may be all these different things can complicate our signal. So our path through all of this is where we know that we are going to be able to see a shift in carbonate chemistry and seawater chemistry in general. We monitor that and we make measurements as far out until we lose that signal against the natural background. So for this pilot that we're working on in Washington, we've been collecting chemistry data for more than a year now. So we have a solid understanding of what some seasonal variations, tidal variations, all of these different things can do to water in our region. And then we continue that type of monitoring in the near field where we see shifts in pH, shifts in alkalinity, and so on. This ties to modeling in a couple of ways. So when we run ocean models, we are effectively trying to quantify how much carbon dioxide is moving from the atmosphere into the ocean and staying there. Those models are used for a variety of other purposes. So in our region, in the Salish Sea, there are regional ocean models that are used for ecosystem management, for understanding fisheries, for understanding nutrient pollution, all sorts of these different things. So we're adding one more facet on how these models can be used by extending the carbonate chemistry that is included. We also have these near-field mixing zone analyses that tell us where this alkalinity is going. And connecting those two dots, the near-field models to the regional models, is not trivial, right? This is something that requires a lot of work and is taking a lot of attention in this field. But as these trials and as these field deployments and pilots advance, we are learning a lot about how to improve this.
So Mallory, I want to go into a little bit more detail about what you shared in terms of the timescales and the processes that you're trying to quantify, right? We've recently shared a blog post on the Crime2Sea website that sort of introduced these different stages of CDR that happen sort of across open and closed system alike, which is, I think, helpful to understanding what is possible to be measured and what needs to be modeled in terms of carbon removal. So these 3 stages that we've thought of, and credit goes to Anu Khan here, is the conversion, the removal, and the storage bit of CDR broadly. You mentioned, you add the alkalinity and it creates space, which is sort of this conversion stage, and also the storage space actually in OAE. And then the removal may happen over longer timescales eventually. Can you share a little bit more about sort of how measurements can play a role in maybe one of the two, or where you see the role of models sort of really fit in?
Yeah. So we certainly appreciate this breakdown because ocean alkalinity enhancement is not something that is intuitive to many people, right? We're talking about chemistry that is quite complicated in a lot of ways, but in others is quite straightforward. We have carbon and it sits in a couple of different forms in seawater. And so shifting carbon between different forms, bicarbonate, carbonate ions, and some of these things are the topics that we talk about technically, but it's really about shifting the way that carbon is attached to other molecules in response to pH in seawater. And that is something that we directly impact when we put alkalinity into the ocean. So this first stage, this conversion and the beginning of the storage piece is really in impacting the carbon in seawater. And that's something that we can measure in the near field. When we release alkalinity into the ocean, we see an immediate increase in pH, we see an increase in alkalinity, and we can track that to some extent. The rest of it, though, the storage where CO2 moves further into this seawater pool and stays there, this is something that happens in nature already. This is something that we have a good handle on from the models. And it's also the piece that is the hardest for us to monitor because over the time scales in which carbon dioxide moves from the atmosphere into the ocean, we've had currents and tides and mixing and storms, and our ability to track that measurement, to track that carbon dioxide is difficult. So in some contexts, you could think about monitoring that. That's if you had a trapped volume of seawater in a lab, we can make these measurements and we can display this conversion to storage step. But as soon as you move out into the field, you really do rely on models. And in that case, your attention shifts from making measurements to track your process to making measurements to validate models. And that's a whole nother can of worms and another whole subject that can be quite complex in some areas. But some things we think about when we're validating models are over the entire region that we're interested in modeling, do current measurements from measurements that are taken across the ocean basin. For us, this is the entire regime from Seattle to Vancouver and out to the coast. Do they match up with what's predicted? Do measurements that are being made by buoys and moorings match up with what's predicted? And so on. So in Washington State, there are two different regional models that ingest all sorts of different data sources, some of them federal, some of them international, some of them small projects. And there are efforts to validate these models in different ways.
Great. I think that immediately gets me to my next question. I really appreciate this breakdown of the usability of measurements and models at different stages. It's such a complex topic for folks, I think, to comprehend and wrap their head around. As you say, it's the chemistry in the ocean is complex. You mentioned it before that there are many different reasons measurements are taken in the ocean. And I want to push you a little bit on that or hone in on this a little bit. Because, of course, in an ideal world, we are taking all sorts of measurements for environmental reasons. We're taking all sorts of measurements to track our process and to validate our models. But at the end of the day, you're a company that needs to, of course, keep financial considerations in mind as well. So you've also contributed to this database that I've recently built and might be out by the time we release the podcast or shortly after, where we're comparing a lot of these different monitoring approaches across trials. And it includes the purpose of a measurement as one of these metrics. I think in your trial design, a lot of the measurements are, as you say, driven by the mixing zone idea and the permit requirements. And then you add on top of that what you require for quantification, what you require for model validation and for environmental purposes, etc. Can you share more about sort of the long-term vision and how you're thinking about sustaining these different measurement scopes if you keep doing them, even if they're not required necessarily from a permit perspective, and how you see this sort of evolve in the future? $1 million question.
Yep, million dollar question with a lot of sub questions packed into there. So the first thing I want to say about this is that every site that we approach is going to be quite different, right? No matter what ocean basin, what coastline you go to, there's going to be a different amount of historical data, historical model data, different contexts of what biology is present, what chemistry is present. They're all going to require specific analysis about what is needed to fill in the gaps. And that's something we all have to face. So to put an example around the site that we're talking about in Washington, we have a barge that is centered on a pier that allows us to effectively walk across our mixing zone. So the infrastructure that's available plays a role in our choice of what sensors we can deploy, what we can observe, how many samples we can take. And we're well aware that as we look from site to site, those types of infrastructure might not be available. So anyone, whether they're a company or whether they're an academic researcher, has to make choices. What is it that is feasible? What can I put in the water and rely on? What choice of sensors will work for a specific range of temperatures and salinities? All of the technical choices come into play. And then there's the role of regulatory and community engagement that might influence our design strongly. So for us, we have to think about all of these pieces and then layer in the business angle, which is if at the end of the day, a marine carbon dioxide removal company wants to sell carbon credits, now there is a registry and a protocol and a verifier that are also looking at our choices. So what we're seeing right now across the field, whether it's ocean alkalinity enhancement or other marine carbon dioxide removal methods, is definitely a preference for throwing everything at the wall and seeing what sticks. And we can afford that to some extent around early field trials, but we know that that's not going to continue into the future. There's every parameter in the world that we might like to measure, we have to decide, is it going to help us in some way? So then we come back to this question of why are we making this measure? What am I going to do with it? If we collect oodles of alkalinity data, then that is directly applicable to our process because we can look at where the alkalinity is distributed and we can use that for models. And then we can think about, well, what about oxygen? Oxygen might help us understand some facets of the natural environment, what biology is interacting in different ways. Do we have confounding factors like hypoxia? Can we put that into models, right? And so we have to go in some cases parameter by parameter and make some judgments around what is reasonable, what is helpful. Another thing I want to say is that the recommendations on what we can and should and must monitor are really recommendations at this point. The requirements that we have to toe the line for are regulatory, but beyond that, there's a lot of moving thought in terms of what we see works and what doesn't, because we've only had a handful of field trials that have measured things. And we know that we can make a lot of predictions about what we should make measurements for. And when we go out to the field, those ideas may or may not stand up. So flexibility at this early stage is really important.
Yeah, can I follow up on that last point? To my understanding, there's also a requirement from whichever registry you may want to put credits on. In the perspective you just shared, would you say that these are still recommended measurements and that can change sort of flexibly to some extent?
Yeah. I would say exactly that. And it's because the prescriptions that are in the protocols are really meant to suit a variety of different technologies and different deployments. So if a protocol tells me we must measure pH at the edge of a mixing zone, it doesn't tell me what type of sensor. It doesn't tell me resolution, frequency. Is it at the surface? Is it at depth? Is it a range of different things? So there's room for interpretation in how these pieces work. And there's a lot of folks who are involved in interpreting what it is that needs to be done. That's scientific advisors, that's verifiers, that's interpretation from academic voices in the community. But we have to be cautious when we look at what are the requirements from our regulatory standpoint, which tells you this place, this time, this frequency. And then we look at other voices that don't quite go that far. And that's right now a good thing, because if we put out a community requirement that everyone must measure pH at the surface at some specific location using some technology, that might not actually work for all projects, depending on what infrastructure is there, what range of variables, and so on. So we really need to work through all of those different pieces. And that's something that we've been doing at our field sites for a very long time to make sure that we're really hitting the needs of our processes as well as everyone else who has a stake in this.
Yeah, I mean, you and I have talked about this obviously a lot already, but this is exactly one of the, I guess, hypotheses that folks who spent a lot of time thinking about this sort of had when talking about sort of broadly, how do we measure CDR or how do we measure OAE in the field? And one of the things that definitely came out of the database that you've helped me build is that even though a protocol might require XYZ, there's huge variation in how it is actually being implemented. I wonder if, before we close it off, you have a hot take on what this will actually look like, though. So how do we make these assessments, and how do we make the tweaks required across trials that have implemented a protocol, that have tested monitoring campaigns differently? What's the sort of agenda, if there is one, in your opinion?
Yeah, in the immediate future, I think all of those tweaks are site by site, case by case basis, and that certainly means that we need a lot of eyes on each process to understand what did and didn't work, and we do need to filter out what are the layers of priority. For us, we certainly put community input way high up on our list of the priorities when we make choices about what we're sensing, what we're modeling, what we're spending our time on. So an example of that, when we're talking about the protocols, Isometric has a protocol for coastal outfalls for ocean alkalinity enhancement that requires measurement of pH and a few other variables at the edge of a mixing zone if you are using a mixing zone. But a mixing zone is not, just a line in the water. It is effectively quite a wide barrier that is depth, surface, radius, circumference around this whole region. And so when you have to decide which portion of the edge of the mixing zone can I spend my funds on? You have to make a lot of choices because we can't have sensors everywhere. That's just not going to work. So in piecing that apart, one thing that we did was we went to community input, and there, like Kyla mentioned, there's a yacht club right next door that runs a community sailing program, and they're our neighbors. And so when they come to us and say, we'd really like to understand what are the changes that may be closer to our operations that may impact us, well, that's great feedback for us to say this sensor should live here on this edge of the mixing zone where we can reach it, where it's accessible, and where it's useful for more than one purpose, because we have limited resources to spread across a whole project here. So that sort of assessment of what is feasible, what might work from what we've learned from other projects, and what are the priorities for all the people who care about a project that is coming into their backyard are really, really valuable.
Yeah, I think that's really interesting, right? The emphasis on this being an organic process in some ways, right? In terms of responding to stakeholder concerns and interests as this proceeds. So Kyla, for those nearby your site in Washington State, as well as those far flung, how can folks stay up to date and follow your trial?
So if you want to come talk to us, hello@ebcarbon.com, always feel free. It'll probably be me on the other end of that, so you know who you're getting. But I think the other important piece of this is that, and Mallory can jump in here, but we're going to be submitting papers on the research that we're doing at this site. And so that's another really important way folks can follow the journey. I don't know, Mallory, if you want to jump in on that.
Absolutely. So I'll highlight a couple of things. A few papers that are going out immediately, as in the next week. There's a special issue on marine carbon dioxide, and everyone wants to put their literature into that. It's because it's convenient to get to and easy to see, right? And so some of the projects we've been working on that we really want to bring to light for this community, one is the salmon study that Kyla mentioned earlier today. This is a project that we worked on with local community, a local tribe, to design a novel methodology to understand what it is that might happen to a salmon if it swims past our outfall, right? So for this, we used near field dilution models. We used measurements in the near field to help design the level of alkalinity and pH shifts that we'd expose live salmon to. And we ran this study in a local toxicology laboratory. And what we come out with, the spoiler at the end of the day, is that there are no impacts on the juvenile salmon that we tested relative to controls, which is great news for us. And it's a good way to think about what are some of the different targets that we can address when there's a wealth of other literature that's coming out about what OAE, what alkalinity enhancement might do to different species. Well, here's what OAE might do to a species that it may be in our mixing zone for some period of time, right? So we can start building off of that. We also have research that's coming out of our collaboration with Pacific Northwest-National Lab down the road. Over there, in the past, we've presented papers on modeling and biological impacts and so on. We have a study that will be soon coming out about the work that goes into releasing alkalinity from trials that we did end of last year and beginning of this year. We also have another study that will be coming out of a collaboration with Stony Brook University, where we've been continuing these experiments in large tanks. What happens if you take a controlled body of seawater and you run this whole process out to really capture the conversion and the removal and the storage in a way that we just can't do in the field. And beyond all of that, we've been progressing in the modeling that we've been doing on a couple of different modeling projects, and that will become available. So our philosophy for all these different scientific targets is come talk to us. We are always open for collaborative ideas and for discussing the research that's been out, and there's about to be a lot more coming to the public.
Thank you, Mallory, for these thorough insights. I think it's really important, and we could keep talking for a long time, but handing it back over to Will to close us out for the episode. Thank you.
Great. I also want to take a moment to mark the passing of Matt Eisenman, one of the co-founders of EB, who inspired so many in the MCDR field. For those of our listeners who didn't know Matt, Mallory, could you tell us a bit about him and his impact in the MCDR community?
Yeah, so Matt was a real forerunner. Before he got into EB, before he started this whole deal with alkalinity enhancement, he worked in direct ocean capture. He's worked in a variety of different fields. He works in optodes, he works in photonics, just a massive amount of interest. I got pulled into Matt's lab when I left my PhD and was looking for a postdoc. And up until that point, I was doing traditional observations in the marine environment, looking at acidification, understanding impacts in the natural environment. And he was really the one who convinced me that there's a role for applied science here, and maybe we can finally do something about all these observations that we're making. So I worked closely with Matt for a year as a postdoc, and then from there on at ACRONYMS. And the thing that has come out of every discussion I've had about Matt with his students, his postdocs, his friends, his family, is that Matt made a space for everyone to talk about everything. He was interested in just about every field of science you could imagine, and he could sit down with a student, an undergrad, another faculty, someone who's in the national academies, and really make them feel like, first, they're coming out of that conversation with a solid understanding of what it is we need to do to progress, but second, their voices are welcome. And so that was really special and important about Matt. His contributions in this field were beyond huge. It's hard to express how much we all lose from his passing. But, we're doing what we can to carry his work forward. And he has a slew of students, postdocs, researchers, collaborators who are really trying to carry his vision forward. Two other things that I wanted to mention. Well, first is Matt really hated the attention that he got on him in a lot of different ways. He was someone who really wanted attention to shine on what needs to happen next and what is the work, and not on himself. He was not all that interested in the amount of focus and spotlight that we have all been putting on him over the past months, but he deserved it. And so one thing we've done to carry that through is the research barge that we have up at this research pilot is named the RB Iceman, which is the research barge Iceman. There's a label on a life vest there that we're all, quite happy about. We also wanted to mention that our CEO at ACRONYMS has put together an endowed scholarship fund at Princeton, and this is aimed at supporting young scientists who are passionate about climate change in memory of Matt.
Thanks for that, Mallory. We all miss you, Matt.
I also wanted to just share that Matt was one of the very first, very supportive people in the MCDR field. For me, a great mentor and all-around kind person. He also once shared a very heartfelt podcast story with me. He said that he always listened to the podcast on his runs in the forest and sometimes needed to stand still to note down a thought. And in light of that, we wanted to close this episode by sharing a little bit of a snippet of Matt's appearance on Plan C from 1.5 years ago.
In terms of EB's kind of 5-year vision, ultimately we would love to get to 1 million tons of CO2 per year removal in 5 years, but that's a very ambitious number, right? That's basically scaling. Yes. That's scaling up 10 times every year from the current 100 tons. And kind of more important than meeting it's important we need to move as quickly as we can to meet the huge problem in front of us. But again, I think we need to lay the foundation first. So kind of that's really the goal, is laying that foundation of quantifying the uncertainty in our MRV approach with partners, publicly validating our efficiency and also the safety, and then making sure once we have the right system, then scaling that as quickly as we can.
So once again, thank you for joining us, Kyla and Mallory. And as always, thank you to our listeners. If you enjoyed this episode, please leave a comment or review and share this episode widely. And with that, we say thank you, and we'll hear you next time. Bye all.
Thank you all.
Thank you.
Thanks.